Hi, I'm Michel-Tyler, and this is my ENME 489Y remote sensing final project. The goal of the project was to build an active remote sensing instrument to map an object on campus and create a 3D point cloud of it. Eventually, this data may be used to create a 3D map of the whole campus. I'll begin by describing the target I chose to map. I'll then explain the instrument and talk through its design. Finally, I'll show the data collection, post-processing, and ultimately the 3D point cloud created. My target was a potted tree near the Clarice Performing Arts Center on North Campus. The plant features a sparse tree inside of a solid symmetrical pot. I chose the target for a number of reasons. 1, because it's on a quiet part of campus. 2, because I was curious about the difference in mapping the sparse tree and solid pot. And 3, because I knew I would be mapping when the tree was in bloom. Now, let's move to the instrument. The instrument uses a combination of a Raspberry Pi for control and processing, a laser line for transmitting into the environment, and a camera for receiving the response of the laser line. The instrument uses active remote sensing because it provides its own signal to measure. It differs from LiDAR because the signal being used for distance is pixel distance from the center of an image rather than the time it takes for light to reach the target and then return. Computer vision was used to locate and isolate the line laser in each image using an HSV mask for that line. A geometrical relationship between the distance from the camera to the laser transmitter and then to the target is used to create a mapping from pixel location in an image to distance in the field. My instrument was built using material I had lying around as well as the electronics needed for processing. The chassis is wood. The camera and line laser are exactly 12 inches from one another. The Pi sits on the chassis and is powered from a 5-volt battery pack. The line laser is powered by a 6-volt battery pack connected to a switch. The bolt allows the instrument to be angled, and a weighted pendulum was used to quickly check the angle. The first and last angle of each trial was verified with an iPhone app as well. The first calibration of the instrument was largely unsuccessful. This calibration was mostly an exercise in getting the laser to show up in the image. The second calibration, however, was far better. Several distances were not calibrated correctly because of the difficulty in finding the laser in the image. From this point forward, a 10-second exposure was used on the camera to improve the laser in the image. Data was collected by running a Python program that captured an image of the laser and target at a specified angle. Between 25 and 30 images were collected for each orientation of the target. I used 8 orientations of the pot and tree bottom, and 4 of the tree only. A total of 319 images were collected for processing. While the pot was straightforward to collect, the tree was much harder due to lighting. To make it easier, I covered ground level lights where I could, and I waited for cars to pass before collecting. Still, 2 HSV masks were needed for each orientation to pick up the laser at all. Once data was collected, an HSV mask was generated to locate and isolate the laser in the image. This was done using a Python script taking a sample image as input. These values would later be put into the data generation file for data generation. Data was generated using a Python script that opened the files from a specified orientation, applied the HSV mask to the open files, found all pixels in the mask, and then calculated a corresponding set of 3D XYZ points to later plot. 3D plotting was done in MATLAB. The MATLAB file used read in the text files as arrays. The data was then concatenated and passed through a filter that used manually found threshold values to filter out noise. The filtered data was then transformed using rotation matrices corresponding to each orientation. My orientations were at 45-degree intervals, so this was fairly straightforward. Finally, the 3D point cloud was plotted. Here are both the filtered and unfiltered point clouds. Filtered cloud shows a lot of noise where the lights would have been showing in the top of the target. The general shape, though, is very prevalent. The filtered cloud, though, is pretty representative of the real object. Some branch structure can be made out, the pot comes through well, and the dimensions are similar. Finally, we're going to look at how we create a mesh out of the 3D point cloud generated. This mesh was largely unsuccessful. So here I am in MATLAB right now using fprint to print my matrix into a text file. Now we're going to open up that text file in MeshLab. So it's an XYZ file because I guess the TXT format isn't supported with the Ubuntu release. Here's the point cloud, so it looks identical to the one that's open in MATLAB. Here's the point slider that just changes the size of the points depending on what you want to look at. The first step is to calculate the normal to the points. Now I had trouble with anything above a normal of, or a neighbor of 1. I'm not sure why it's showing up, or not sure why it's not showing up here, but the normal with 100 was wild. So changing it to 1, applying, hitting OK. Next we want to create the mesh, calculate the mesh. So we're going to use the Poisson, just using the typical values. And so here is the mesh that is resultant. It's a silly bulbous looking thing with that manifold kind of in the middle. The way to get rid of those extra surfaces is to use the rectangular face select tool. Unfortunately, with the Ubuntu release of this software, there seems to be a problem with the graphical settings where you couldn't select. Now, after about an hour of searching for a solution online, couldn't really find one. So for this video, we'll have to ignore that. The final steps to this process are to export as a .ply. The point cloud in MATLAB was far easier to see what was being mapped than this mesh. As we approach the end of the semester, the immediate need for an improved point cloud is pretty obvious.